In today's video, I'm excited to show you a USD-based workflow to create an animated pendulum system in Houdini and export it to Reality Composer Pro for deployment in RealityKit. You are seeing the final render running in augmented reality on an iPhone. Thanks to RealityKit's cross-platform capabilities in iOS 18, this same scene will work seamlessly across iPhones, Vision Pro, or macOS without any modifications to the asset pipeline. Our workflow in Houdini will consist of three components. First, we'll procedurally create the base pendulum geometry. We'll start by building a pole and frame using basic shapes and extrusions. Then we'll create the pendulum ball as a subdivided icosahedron. To ensure we have control over material assignments later, we'll create separate name groups for the frame and the ball. We'll create a line with 10 points to position our pendulums on. We'll then instance our pendulum across these points, making sure that the pivot points are correctly set. After that, we'll create our animation and prepare it for RealityKit. We'll generate a cascading wave motion for our pendulums using Houdini's chop network. To maintain compatibility with RealityKit, we'll set up a clean USD hierarchy with a root object. Finally, we'll package and export everything as a USD file that RealityKit can understand. Once we move to Reality Composer Pro, we'll import our USD file and verify that the animation is working correctly. We'll set up metallic materials with different color variations, and thanks to the separated USD primitives, we'll be able to independently assign materials to the frame and the ball of the pendulum. The key to this workflow is maintaining a proper USD hierarchy throughout the pipeline from Houdini to Reality Composer Pro. So without further ado, let's get started. We are now in Houdini. We have our 3D scene over here in the viewport. And we're currently at the stage network layer. And we can see that we have two nodes. A scene import node responsible for fetching the entire scene, and a USD render operation node responsible for writing the 3D scene to a USD file that we can then import into RealityKit. To understand how this 3D scene is created, let's go to the object network layer, and we can see that we have two nodes here. A pendulum's sim out node and a pendulum node. The pendulum's sim out node is responsible for instancing the pendulum and animating it. And if we go to the first keyframe and actually turn that node off and turn the geometry node pendulum on, we can see that this node is responsible for just creating a single pendulum, a single piece of geometry for that pendulum. So let's have a look at how that actually works. To do, let's start here at the top. Let's turn on the first element starting from. We have a circle that serves as the base shape for the top of the pendulum's frame. We can use a poly extrude node to create a thin cylinder forming the top frame's structure of the pendulum. Once we have the poly extrude node, we can polyfill it. And what that does is it will, if we look at the bottom of the geometry, we can see that polyfill will close the object so that it's solid. Then we can use a transform node, which I don't actually know if is still required. It doesn't seem to be doing anything, so let's delete it. And then we have a soft peak node, which will scale down that shape along its normals. So we can basically make the line thin. Then let's look at the other half of the equation. Starting with a torus. So we have a torus right here, and we can use a soft peak node to also scale it down. And then we can transform it slightly. And then once we merge it, we can see that we have this pole with the frame here. So this is like what it will look like. Once we have that, we can give it a name. It was called the attribute frame, and let's give it a name frame. Then we can group that together. Let's have a look at the right side over here, because we'll end up merging that right side with this frame. What we still have left to do is create the actual ball in the center of the pendulum. To do that, we're going to start with a platonic node here, and we'll make it a icosahedron, and we can subdivide it. And it's currently set to 2, but we could do 4, but 2 should be fine. And we'll give that a name and a group, and we're going to call that name, that attribute name, and then the name ball. And then in the group, we can call the group name ball. In the merge node, we can merge our frame with our ball and transform it so it's rotated on the y-axis, pointing forward if we go to our default position here. And then we can write that out to basically this null node, and we'll label that pendulum geo down here. Okay, cool. So now that we have our single piece of pendulum, we can go back and take a look at the pendulum sim out node. We're now in the pendulum's sim out network, and let's see how this node is created. The first thing we do is start with an object merge node. This object merge node pulls in the geometry of the single pendulum that we just created. We can see that it's referencing the pendulum underscore geo node that we just created. And then we can use a pack node to pack it, which is important because it packs the geometry into a single entity to optimize performance and simplify instancing. And it's also very important for RealityKit because RealityKit does not support vertex animations. So we need to pack the geometry so that the animations are created as transform animations. Once we have that packed pendulum, we can look at the right side of the network here, and that is going to be just a line that we can see. That line has a length of 20 meters. It has 10 points, which will ultimately mean that we have 10 pendulums, and then the direction is down -1 on the z-axis. So once we have that line, we can create this node called attribute Wrangler. This node allows us to write a vex expression, which is the scripting language native to Houdini. In this expression, we're creating an attribute called rotation. We are setting the initial value of that attribute or variable to the constant pt_num, which is the point number in the line. If we look at the attribute node here and go into our geometry spreadsheet, we can see that we have a rotation attribute, and the value of that rotation attribute is set to 0 to 9, depending on what numbered node it is. If we go back to the scene view now, we can see that we have this node here called toChops. And I'm just going to get into that in a second, but let's first have a quick look at copy to points node. So copy to points node will then take our pendulum that we've imported using the object merge and place an instance of that pendulum at each point on the line we created. So what we end up is with a straight line of pendulums, every pendulum at the point on the line. And we can transform the pendulum. For instance, if I were to create a transform attribute and I were to make that what we render in the viewport, and I were to go up here to that transform attribute and go to rotate and set a value of 45, we can see that we're rotating the pendulum 45 degrees on the z-axis, but it's not rotated like we want it because we need to set the pivot point to the top of the pendulum because we want to rotate it at the top. So if I set the pivot point to 30 and we zoom out, we can see that we now rotate the pendulum correctly. And the reason this value is 30 is because the geometry that we just built in the geometry network over here when we look at the initial line, or rather the extrude node, we can see that we're setting a distance of 30, which effectively means that the pendulum is 30 meters tall. So let's go to our pendulums set node here, and I'm going to delete this transform. Before I delete it, what I'm going to do now is walk you through the chops portion of this. And chops is the channel operator network in Houdini, and it basically allows you to operate on an array of numbers, and it can represent anything. And so it gives you a lot of freedom in creating and manipulating channels of data that you need to basically perform operations with. In our case, the operation is rotating each pendulum in a way that, oh, interesting. What went wrong here? Oh, we rotated it by 45 degrees. If I bypass that node, we can see that we're back to our rotation that we wanted to have. But let's go back to the transform node. Let's see the rotation here at 45. So let's now delete this node, because now we want to actually figure out how to set this. And to set this, what we're going to do is we're going to take this node, copy 2 points, and we're going to create a for each loop or after it. And in that for each loop, we're going to transform each pendulum. And we can see that if we now go to the output, we can see that we're back with our animation here. How do we set a transform value in here? What we're doing is we're saying rotate the pendulum based on this expression up here. And the expression is 0.0 instance point rotation 0. And what it's doing is it's actually getting, if we look at the geometry spreadsheet again, we can see that we are basically setting, there's different rotation values that are being set as we animate through the timeline. And we want to assign that rotation value that we just saw. We want to apply that to the Z value in the rotation of the transform. And that expression is point. And then here we can call instance point, which gets us the current index in the loop. And we can read the rotation attribute. The rotation attribute is what we created earlier in the attribute Wrangler. So now that we have an attribute that we're rotating, the question is, how do we actually create the values that we want to set the rotation to? And the answer is that we want to create a wave to animate the rotation in and create a looping wave animation. And what we're going to use to achieve that is chops. As I said earlier, after we create this node attribute Wrangler, we now have the rotation attribute. And we have this node here called toChops. And now we can go into the chops network, which lives over here. And in this chops network, we have a geometry node. And this geometry node is responsible for importing data from our upper level, from the SIMOUT level, or rather in Houdini lingo, it's called the SOP level for surface operators. Right here, we're in the chop level for channel operators. And we have the geometry node over here, and the geometry node has an attribute scope called rotation. So it's going to get the rotation attribute from that SOP. So we can see that the SOP here, surface operator, or the node where we have our geometry. And we want to reference the toChops node, which is the one we have right here. So in chops, we're referencing this node. We can go to the we can take a look at this node. We can see, let me not here, I want to look at the geometry spreadsheet. In there, we have the rotation attribute. We're now in the chops network and we're importing the rotation attribute. And then we want to add that. Then we basically need to figure out how do we combine that rotation attribute with its initial value, which actually represents the offset, and then combine that in creating a wave that is offset. So if we have a look at this wave node over here, we can see that we're in the waveform, we're creating a sine wave. We could create a constant wave, which does nothing. A Gaussian wave would look like that, a triangle. So really funky stuff. And what we could try to do is we could, for instance, export variations of that. But for this right now, I want to create the sine wave. And I'm just setting a period of 4. And the key that I need to do in order to achieve the offset here is that I want to set a variable phase parameter in the wave so that each pendulum is at a different phase value. If I were to set this to 0, everything would rotate in unison. If I were to set that to 0.5, that too. We can actually take a look at the motion FX view. We can see that we have basically what appears to be a single line or a single animation curve, but there's in reality 10 animation curves for each pendulum. So if I comment back the original code, which is $C times 0.01, what it will do is it will slightly offset these animation curves. And $C references the channel index, and we have 10 channels, which are created by saying channel name is equal to phase 0 to 9. So what we're effectively doing is we're creating 9 channels. If we can go on that wave node over here, we can see that in the kind of like information part, we have phases 0 through 9, and we can see that we have a minimum value of 40 and a maximum value of 40, and there's some floating point imprecision, but we can see that essentially they're all going from -40 to 40. And we have, slightly different values here, or rather we're creating a channel for each kind of wave value. So let's go back to our scene view now, and we can see that it's animating as we expect. So now the question is, how do we create a channel and write that back to the overall pendulum simulation? To do that, we will take the geometry and the wave, and we will go to this math node right here. And the math node will do some math on those 2 channels that are coming in. We have the channel representing the rotation on the left, which is basically a channel for each index, or a channel for each pendulum, and where we have a channel with values of the wave for each pendulum. And then in the math node, we will actually also have to add a pre-add to subtract the channel index from each channel, because if we look at the channel that we're importing, the channels that we're importing from geometry node, we can see that we have values that are 0 to 9. So when we're doing the pre-computation here, we're essentially saying that for every channel, we want to subtract the channel index so that we basically have 0 as the left value for the channel, and then the right value of the channel would be the wave that we're creating using these different offsets. So then once we have that wave, we can write that out to this null node right here. And once we've written that out, let's have one more quick look here at that node. We can see that we have values here from -40 to 40, and we have different current values: 15, 12, 10, 8, 5, 3, 0,
And at that point, it represents the rotation that we want to set for each pendulum at each frame. So going back up to the pendulum simulation node, for each loop, we have this transform. And in that transform, we have our Vex expression. That Vex expression is, excuse me. I forgot an important part. Let's have a look at this channel node up here. That channel node up here is actually referencing it is referencing the out node in the chops network. And that node, we need to set that to animated. And it's essentially writing it to the attributes rotation. So we're now pulling our channel data from chops and we're setting it as an attribute on our current geometry. And then down here, where we look at the geometry spreadsheet, that we can see that we have the rotation values already on this node. And then pendulum, we will basically update the transform with that rotation value. And then lastly, we can write it out down, and what we're left with is our final animation. So then we can now we can enable the simulation out, and we can from here go to the stage level where we then import, let's expand that. Here we can import the USD pendulum animation. Excuse me. In the scene import node, we can see that we import the pendulum simulation out node right here. And we need to set a root object. This is important for RealityKit so that all our USD data is written under a global root object called OBJ in this case. That is important for RealityKit compatibility. Otherwise, it might cause some funkiness and it's a little more difficult to work with. And then what we also need to do is we need to, I believe, flatten our hierarchy here. So that's important. And then over here in our USD render operation, we can see that we're writing it to this output file called hip USD pendulum animation, which just references our project. And then if we actually go to our root folder where the project resides, we can see that we have a USD file. After we press save to disk, we now have this USD file here called pendulum animation. And we can even preview it in the Finder. But what's cool is that we basically can now go to Reality Converter and we can import it, and we can see that we have our 9 pendulums that are animating. We don't have materials assigned on them, which is why they appear like this. But the crucial thing is that this is running now in Reality Converter, which is a very good sign on the way to bring that pendulum animation into RealityKit itself. So the next part of this is going to be going to Reality Composer Pro, importing this geometry with the animation, assigning materials to each pendulum so that they have cool visual effects. That's what's next. Okay, we are now in Reality Composer Pro, and I've put together a scene with the pendulum, which has materials assigned to the pendulums. We have a red, yellow, and green sphere. So let's have a look at how that works. We have this USD file, which we exported from Houdini. We can go to Reality Converter and see that we have this file, and we can export it. I'm just going to call it Pendulum Animation 1. I'm going to save it to downloads, and I'm going to go back to Reality Composer Pro. I have a new scene over here that is empty, besides the fact that it has 4 materials that I have created: blue, green, red, and yellow. So I can drag the Pendulum Animation 1 file into the view so we can see it in our scene. And if we click on pendulum, if we click on that object, we can drill down and we can see that we have 10 objects. The issue is we don't have the level of granularity required to set a material on both the ball and the frame independently. And so we have to update our Houdini asset in Houdini and then re-export it. This is one of the nice things about Houdini in that it has really good USD support. And frankly, one of the reasons I prefer Houdini over Blender when doing this type of stuff, because it's easier to have greater control over your USD file, which is very important when importing it into RealityKit. So we're going to make an individual object for both the frame/line of the pendulum and the ball. To do that, let's head back into Houdini, go to our object, and the pendulum's sim out node. Go to this pack node, which creates a single instance of pack geometry with everything that is inside the pendulum node. And then also in the copy to lines node, there's this option to pack an instance. So we can turn that off. We don't actually want to pack an instance. And when we do that, we can go down here and once we've turned that off, delete the pack node as well. And so when we delete the pack node, everything becomes very slow. And that's because this is now rendered using vertex animations. We're actually transforming every single point. So it's actually highly inefficient. And that's why it's rendering so slow. The performance is really bad compared to packing it. But we still want to tap into the benefits of packing. We just need to do it at a level lower in the stack before we assign the name to each individual object, which we can set a material on. So going to the pendulum node, we go to object and then a pendulum, and we see our pendulum now in the viewport. We can go to the place where we're creating the name and the group for this first pendulum. In the name, I want to rename that to name because we want to set the name attribute to be frame. And then what I can do is I can do shift and look for the pack node and I drop it in between the merge and the name. And I want to do the same thing over here on the right side for the ball. Once we do that, we can go back to our simulation and see that it plays smoothly again. The reason it plays smoothly is because we now have two packed pieces of geometry, the frame and the ball, and we can export it back at the stage area. Let's actually call it pendulum animation with ball and frame. And we can save it to disk. Now that we've saved it to disk, we can go back to our Finder and see that we have this so the pendulum animation with ball and frame. And we can open it in Reality Converter. Over here, we can see that the animation still plays fine. We can export it and keep the name. From here, we can head to Reality Composer Pro and drag in our asset from downloads. So now we have pendulum animation with ball and frame. Let's go back to our scene_YouTube and let's delete the asset that we just imported, pendulum animation 1. And let's actually just delete it altogether because we no longer want it. And let's drag in pendulum animation with ball and frame to the root. Now we can expand it and see that we have an object for the 10 frames and an object for the 10 balls. And as I said, I've already created materials that we can now assign. I can go to the frames 0 to 9 on the right side to the material binding section and assign it root blue. Now we have the material assigned to the frame. And the material blue, we can take a look at that. When we tap on the material, down here we go in shader graph. We can see that it's a simple shader where we set a color, in this case, kind of like a navy blue. We have metallic set to 1, roughness set to 0, which makes it very shiny, and an index of refraction is 1.5. The green, red, and yellow shaders are doing the exact same thing, just with a different color. So now we can go to ball 0 and set it to the green material. We can go to ball 1, we can go set it the yellow material, and we can go to ball 3, and we can ball 2 and set the red material. And we can keep doing that. And what we're ending up with, if we keep doing that, is this scene right here, where we have all the materials with the level of detail that we need, where we have an object and a ball individually defined in the USD hierarchy, and we can play the animation. From here on out, we can take that Reality Composer Pro project and import it into RealityKit to run on iOS, macOS, or VisionOS.